everybody. Welcome back to me. Thanks. I hope you all had a nice week and a nice MLK day. So it kind of feels like we haven't seen each other for a while. But here we are, back on another lecture day. A couple things just want to say right at the beginning. The lecture from Wednesday will be done today from 4 to 5 here. So don't worry if you're not here. You're out having great plans for the weekend. That's the makeup lecture. It'll be all online. So I might have a 0 audience, and I'll just tell jokes to myself. I do that all the time anyway. So, but at least at home you'll get to see them. Second thing I want to announce is about 2:30 today in Kane, 210. There's a lecture that's called the Math Across Campus lecture, and it's being done by this guy Meyerson. He's from the University of Chicago. He has a Nobel Prize in economics, and he's going to be talking about mathematical models in economics. So if you got that open, and look, you go 2:30 to there, and then you come here for jokes afterward. I clean up afterwards with some jokes, and you go home for the weekend, completely and intellectually filled to the brim. Okay? So anyway, keep that in mind. It should be really good. He's kind of famous. I suppose that's why you get Nobels. So there you go. All right. Now we're going to continue on talking about the kind of ideas that you already have in mind, which is time frequency analysis. Okay? And in particular, you've already been doing this example of your dog and trying to image this marble going through the large or small intestines of this dog. I don't know, do they have large and small too? Like they do? Okay, because cows have lots of intestines, right? I mean, dog. Okay, like 7 stomachs and all that too. Your dog might be saved, hopefully, by you understanding that problem. Imaging, filtering, doing some things like this. Now, let's talk about some of the limitations of that application that's radar versus other applications that are generic to sort of time frequency analysis or processing. So for instance, I might be looking at some signal S in time. And let me just draw some signal. The great thing about doing this is it's really easy to draw, and then you try to make one of these on your computer to make a plot, and you actually have to kind of come up with something. But it's a lot easier to freehand it than to make one on the computer. But suppose this is a signal, and suppose this is even a song. Like maybe it's AC/DC, and you listen to it, and this is the whole AC/DC song, all, let's say, 3.5 minutes of rock right there. Okay? All right. And you want to analyze the signal, or maybe you want to digitally remaster it. Okay? Although we know that they don't need to be digitally remastered. You just turn it up loud. Okay? And that's all you really need. But suppose you were a purist and you wanted to do this. Now, here's the thing, what we have so far. What we have in Fourier transforms is we have this idea that I can then turn this into the frequency content. Right? I can take this signal that I get, I can Fourier transform the whole thing, and what I can get is, as a function of omega, or the frequency components, I get S hat omega, and it has some spectral content. Say something, whatever it happens to be. All right. Now here's the problem with what we've been doing with Fourier transforms. When I look at the song and I Fourier transform it, what this gives me is all the frequencies present in the song, the entire song. However, it doesn't tell me when they were played, right? So, yes, I have drums that are in the background with a certain rhythm, and it's going to give you some Fourier content at some place in frequency, but it doesn't tell me when the note was played. And that seems kind of be an important thing, right? To rock out correctly, there's a beat that goes there, right? So you can do this with your head, right? So that's lost when you do this Fourier picture, all right? All right, so really the underlying issue here then is the fact that when we did the radar, there's 2 issues that were important there. One is that basically what I gave you or what we started looking at initially, was stationary signals, signals that didn't change in time. So you just sit there and detect them. Since they don't change, right? The idea is if you have a stationary signal, really what this is saying about a stationary signal is that the spectral content doesn't change. So typically, this is some kind of periodic signals that don't change. You have something that emits a periodic signal. It always has the same frequency components. That's considered a stationary signal. The fact is, most signals are not stationary. They're non-stationary. Right? How do you like that little clever twist of play of words? Put non in front of something. Non-stationary. And that's kind of generically what you get. The problem with non-stationary signals is what? Now it's changing in time, and it can also be evolving, in frequency. So, for instance, let's come back right over here. The frequency components as I go along this song change. The time evolution of the components changes. Time and frequency are both changing, okay, as the song goes along. So the frequency content here, like let's say when someone's singing a high note, would be very different over here in the guitar solo, let's say. Okay, right? You're going to have different frequency content, and it's going to change. But in our Fourier transform method, it doesn't really account for that, because all it's just going to give you is here's all the frequencies present during the whole thing. It doesn't tell you when or where, and that's a very important part. Now, by the way, in our dog problem that you're trying to save, right, what we do know is that the frequency content is sort of stationary, right? We are sending out omega naught, and we're receiving back omega naught. So at least I know that the frequency hasn't changed. But already in that problem, you realize if I move this thing around in time, the Fourier transform, unless I do the filtering, the Fourier transform by itself doesn't help me. I've got to filter this thing out, and by doing that, then I can follow the path of this marble going through, right? Okay, so I do have at least one part that's stationary. That's the frequency content. But most applications, too, the frequency drifts around in time as well as time. So here's the bottom line. Fourier transforms are kind of useless in this context to really get the kind of information we need. Okay? So non-stationary signals, Fourier transforms, really are not appropriate. It's not an appropriate way to analyze this stuff, okay? Because you lose all the time information. Okay, so how can we change this around? How can we use some of these ideas still? Because it's still very helpful to think about things as time and frequency content, right? So it's still useful. I mean, we're not saying that it's not useful to think about things as having time and frequency. We're just saying that the Fourier transform just, if you get all the spectral content, you lose complete knowledge of where this stuff happened in time. Okay? All right. So here's our options. One option is to think about this. Non-stationary data doesn't work. Stuff that keeps changing in time and its content in time is really hard for a Fourier transform to handle. Well, why would I Fourier transform the whole song? I could come back here and I could say, how about maybe over small sections, smaller windows, I could think about, well, maybe the signal in that smaller window is sort of stationary, at least in that window, right? So I could say, in this interval of time, my signal's not changing a whole lot, so maybe I can kind of use that Fourier transform idea right here in that window to think about different windows give me different stationary signals, essentially. Okay? And then I can say, I'll measure out the Fourier components of this part of the song, this part of the song, this part of the song, and so forth. Okay? All right. So that's really kind of one of the ideas you want to use here. Now we're going to generalize this next, which is to say, all right, so maybe I can do this, but a more general way to think about doing this let's take our signal in time, By the way, for those of you who are actually collecting data, the time series, this will be terribly relevant for you, right, about how to analyze this. Right? I made the song as an AC/DC song. You probably actually have something maybe more important to look at. Like, I don't know, Byron, what are you looking at again? Stuff? So you might have stuff to be looking at, okay? You know, you have some signal. And you have all kinds of frequency components in here. And the key idea is then to say, okay, I want to take up pieces of this, but let's do it in the following way. Let's take a window of time, just like we did here. So for instance, why don't I just multiply this by some kind of Gaussian with some width. Let's call it A. And let's make this function. It could be a Gaussian, it could be anything. But let's make some function G that's going to be some like localized window. It's going to pull out some information in a window here. And I have a parameter tau. And what I want to do is, that's going to be the tau parameter tells me where I'm centering this window. And what I'm going to do is move this window continuously down this signal. Okay? That's called, it's like a filter basically, right? But the filter now is being applied in the time domain. What I'm doing is looking at little sections of time, calculating the spectral content, shifting it over, shifting it over, shifting it over, and I shift it all the way through this signal, and then I can map out the frequency components as I move across this signal. Okay? Does that make sense? Okay. Yeah? No? No response. Excellent. I'm going to assume that it's so obvious then. So, by the way, this is not a new idea. People really realized very early on the limitations of Fourier analysis on signals, aside from stationary processes. So if you go back to this, historically it's back to Gabor, 1946, where he started thinking about these ideas. 1946, an interesting year. If you look at the historical development of technology, this is about the time when sonar and radar started playing fundamental roles in science. In fact, the British were able to basically repel the Germans from invading England because they had radar technology. Okay? So that was starting to develop right around 1944, 43. And the Germans were always like, how do they know where we're going? Every time we go launch something, they know where we're going. So at first, at that point, because they didn't have technology, it's like we must have someone squealing somewhere, right? But it was more than that. They did. They had the skies, the airways, the microwave. You know, they were doing radar detection, and they would say, there they are. Let's launch. Without that, by the way, I think a different ending, at least there, okay? Because that was pretty critical. So 1946, they already saw the power of this, started developing these ideas. They already knew the limitations of Fourier transforms in terms of localizing where things are. And so you kind of come up with this more general idea of let's put a window on it and go across. And so what Gabor said is say, look, now what I can do is I can localize in time. And essentially, when I Fourier transform this, I'm going to get the Fourier components that are sitting in that window. So I'm localizing also in frequency. Okay? So Gabor came up with this idea that I'm going to define some function. Let's call it GTW. And this is essentially going to be my new Fourier kernel in a Fourier transform. Okay? This is the typical Fourier domain kernel, right? You just multiply by e to my omega t, transform, you're done. Now I'm going to add to it this time filter, which is localized around some frequency. And I'm going to define the Gabor transform. As the following, the Gabor transform of some function f. By the way, when you Fourier transform, right, here's the big deal. When you Fourier transform f, the Fourier transform f is simply a function of omega only. Right? When you Fourier transform a signal in time, it becomes strictly a function of frequency. Now, in this method, this becomes a function of both frequency and time. So you preserve, somehow, both information about the time localization, space, and frequency localization. And that's what we're going after here. Okay, and the definition of this transform is fairly straightforward. Let's call it F tilde. I usually use hats for Fourier transform. The little tilde will be the Gabor transform. The G for Gabor is the following. Negative infinity to infinity, e to the minus I omega tau, f of tau, there is the definition of the Gabor transform. The bar represents complex conjugation. Okay? And so the idea is I say, without this, that's just the Fourier transform. That's all it is. With it, now this localizes in time, and what I do now is I integrate over all of tau. In other words, you see this tau right there? I slide it around. I slide this thing through the whole signal continuously. So I take this little window, and I slide it down, and I produce an integral, continuous. Of course, obviously, when we do this, we're going to do a discrete version of it because, right, you're going to, even the Fourier transform, in principle, it's an integral, but really what you do is you do a finite number depending upon how you set up your discretization. But there you go. Let's just slide this around. And now what I end up with is information about frequency, some f tilde, which is going to give me time frequency information. Okay? Another way to write this is just simply an inner product of f g bar tw, or if you like your bracket notation. Anyway, these are just different ways to think about writing that thing. Edwin, what did I write wrong? Did I write something wrong? I just can't, you can't read it? All right. Okay. There, that's the key idea. 1946 had a big impact because now you start, for the first time, having this idea of a way of representing signals in time and frequency jointly, distributed somehow. Okay? So that's going to be important for analyzing any kind of information you have. It gives you localization in time, and for each localization in time, I get the frequency content of that piece of time. Okay. Yeah, Jake.
So is the top equation, is little g, is that always even about t equals tau?
Doesn't have to be. Okay, so here's one comment about g. At this point, you think about g just being some kind of localized function. It can even be complex. You can make up g to be almost anything at this point, right? It's very generic. Except what we would like it to do is sort of something that's sort of localized. All right? The standard thing is going to be to take something real and symmetric. But generically, you can take it to be most things, as long as this integral is finite, essentially.
Well, the reason why I ask is because it seems weird that you said tau minus t instead of t minus tau. I mean, it wouldn't make a big deal if it were even.
Oh, actually, it is tau minus t. Sorry. Thanks. So yes, to your question, it is tau minus t. Asked in a very circuitous way. But that's what you were asking. Everybody good? Okay, there we go. Let me change that around. All right, so there's the definition. There's this. By the way, let's talk about Fourier transform windows, or let's talk about these Gabor windows. I drew a Gaussian. Part of the reason I draw a Gaussian is because with the Fourier transform, there is a Heisenberg uncertainty relationship. The more localized you are in time, the broader you are in space. The more localized in frequency, the more localized in frequency, the broader in time. But the Gaussian has the minimum time bandwidth product. You get the best frequency and time resolution together if you use basically a Gaussian. Okay? At least in our standard way of thinking. We're going to talk about wavelets a little bit later, and wavelets are a little bit different beast, but still very nice. But I don't have to use that. I could use things like this. Square filter. Often called a Shannon filter. Idea is, take this out. You don't. It's compact support. In other words, it's 0 here, 1 there. That's the function. And you slide that thing back and forth. Okay? But when you Fourier transform things like this, the sharp edges actually create high frequencies. So there's a little bit of a stupidity there that happens, right? Unless you take care of it, right? Because now you're cutting off that signal right there. You're making a discontinuity. Discontinuities in Fourier domains, what do? They generate high frequencies, Gibbs phenomena. Okay? So typically people like to do things like this. You could do something that's asymmetric if you had some reason to do that, right? You can make up almost anything. But let me tell you some properties of these things that are useful for us and also for setting the framework to start thinking more broadly about what's called time-frequency analysis. We've been doing time-frequency analysis with Fourier transforms, but time analysis or frequency analysis. This is time-frequency together at the same time, looking at how they both are evolving in some sense together. You have information on both, not one or the other. Okay? So let's start off with a couple properties of this thing, and we'll move on. Okay, so first, start off with this. If G is real and symmetric, further, let's start off with something like this. You normalize it. You say the area under this filter or Gabor window is 1, and if you slide it, tau minus t, that's also 1. So no matter where you slide this, the area is 1. Okay? So in other words, this filter doesn't really depend on where you are in position, right? Because you can make it a generic function of t minus tau, but the point is, it's just a function that's centered around t minus tau. It doesn't change as you change that. Then the definition changes slightly. To this. It's really the same. I just took the complex conjugate off that G. Okay? This is called the short time Fourier transform. Okay? The Gabor transform, or the short, there's a lot of different names. Short time Fourier transform. In other words, you pick the window of time. You have a lot of data over a long period of time. You picked a short window of it, and you slide that window around. Okay? Short time Fourier transform. And essentially, what this does, it localizes the Fourier modes. Localization, localization, around t equals tau, right? This thing localizes your Fourier content around t equals tau, and that's the important thing that it does for you. Okay? A couple things to note about this short-time Fourier transform. First, the energy is bounded. So, if you look at this thing by what's called the Schwarz inequality, what you can find is this is less than basically the F and G. Okay? That's one thing. Here's another one. The energy around some point time and some frequency omega is just simply given by the following. You can actually calculate this out to be absolute value. So this is before you do the inequality. That's just to show it's bounded. But here is the interpretation of what this integral actually means. What this tells you is when I calculate the absolute value squared of this transform and I plot it in time and frequency, what it tells me, when this is the definition of this thing, it tells me how the energy of this signal is localized around some time t, some frequency omega. Okay? That's what that tells you. By the way, one of the important quantities to calculate is, all right, so it's localized around this point time and frequency, but one of the things you often want to know is how well spread is that energy around this localized point? Is it like, well, here's the local point, but energy goes all over the place, time and frequency? So what you're really asking there about is the variance, right? How wide is my spread of energy around those points? This is the mean. And the variance of these things, you can calculate these out. Call it sigma t squared is equal to, you're calculating basically a second moment, tau minus t squared of g t w. Okay, and that is basically tells you how tightly localized in time it is. And to get it, the localization and frequency, here is the calculation. The hat denotes Fourier transform, by the way. So you take this Gabor window, G, you Fourier transform it. It now tells you what this window looks like in the Fourier domain. Take its absolute value squared, integrate against nu minus omega. Nu is just another, oh, I need to integrate over all nu. Okay, and that tells me it's localization and frequency around that point. Okay? So these are good properties to know, right? One thing you want to know is if I have signal and I'm very interested in a particular signature of frequency and time, this tells me I can look at that thing, I can calculate the energy there, but it also tells me how tightly localized it is around that spot by just simply calculating these quantities. Okay? So that's important. The other thing that's very important, and we shouldn't take this for granted because I'm going to show you some of the other, I'll just hint at some of the other available time frequency type transforms available. But this one here, it's also linear. It's a linear transform. So in other words, you say I take the Gabor transform of A plus AF1 plus B F2, where A and B are constants and F1 and F2 are two things. Now, normally we just take this for granted in Fourier transforms. Is that, well, that's just easy. That's, of course, the Gabor transform of F1 plus B times the Gabor transform of F2. Okay? That's the linearity argument. Not all these time frequency methods are linear. And so it's important to realize that this one is. One more. How do you find the inverse? So let me write down the complete short time Fourier transform or Gabor transform pairs. Okay? All right, so we already know that the short time Fourier transform is equal to the following. It's just like the Fourier transform, except for now you got that extra piece in there. So now this becomes a function of both time and frequency. And to undo it, to get back to your original signal, it's called f tau, is equal to 1 over 2 pi, 1 over you'll notice some extra features here, very different than the Fourier transform. So first, using the Fourier transform, you put it in frequency space, right? So you put it over there in the frequency space, and so all you have to do is integrate over all the frequencies to get back in time. Well, now you have to integrate over all these frequencies, but then you also have to say, well, yeah, but I did this space time frequency representation, so I also have to integrate over all the time I did. So you integrate first over your frequencies, and then you integrate over your time to produce a function of tau. Okay? Short time Fourier transform, it's inverse. Just like the Fourier transform, we're just going to call these functions. Yeah.
So 2 things. So does that order matter, that you do integration over frequency, then time?
It depends a lot on how you pick g, right? It's just like any double integral. Look at what your function g that you specifically pick, and also what your function f is, right?
And then the way you have that written there. Oh, do you mean that infinity and negative infinity are over both integrals?
Yes, both integrals. Yeah. Yes.
In the Gabor transform, there's the exponential term.
Yes.
Is that supposed to be tau or t? Because on the right border, you've got tau.
I think it's supposed to be tau. Sorry. In the notes, once they're typed up, you see this? Written at 35,000 feet on a bumpy plane ride, right, Dedwin? Yeah? So the handwriting doesn't always come out. You're trying to just get the, before you get a next bump, you try to write it down. But I think that's a tau. Yeah, 'cause you do that and then you just shift the t's, right? And it gives you something. Okay. Okay. And if it's wrong, I'll have it correct in the notes. Okay. So there's the Fourier transform pair. And now I'm going to paint you a picture. Now, the picture is worth 1,000 words. Because the picture starts putting in your head, hopefully, the context under which you want to start thinking about this stuff. All right? So let me erase this stuff over here. I'm going to basically make 3 pictures. You have information. You have a signal in time, right? And you are trying to gather out of that signal in time meaningful information to say something, right? Here's a picture for you. We know that for every signal, we have some time, potentially frequency representation of this thing. So let's put time down here on this axis. And frequency there. Behind one of these is a goat. I'm just kidding. Okay. All right. 3 doors. So let's talk about, first of all, you have different methods. You have time series analysis, right? You have what happens in time to a signal. There are other things you can do besides Fourier transform it. You can do, okay, autocorrelations, correlations. You can just take this data and do all kinds of time manipulations of this time series. Okay? So what you have is essentially, you are, in the time series way of thinking about it, you are actually gathering up a lot of information about different points of time. So let me draw this like this. So you have some time resolution, but if you stay in the time series way of thinking, you never gather any frequency resolution issue. You don't gather anything about the frequencies. So in some sense, you can say, what are the frequency? I have no resolution of the frequency. What about the Fourier transform? Fourier transform is opposite. The Fourier transform says, I'm going to transform this out. I'm going to collect I'm going to bin everything up into frequencies. That's all I do. Fourier transform says, once you do that, you've lost all your time information, right? It's a different picture. It's like this. You've binned up your frequencies, you've taken your time signal, and you've thrown it up here, and you have information at every different frequency. You have no idea about what's going out in time. Okay? By the way, these are two opposite ends of the Heisenberg uncertainty principle. Heisenberg uncertainty says, for in the quantum mechanics, so basically in quantum mechanics it came up because basically in quantum mechanics the Fourier transform plays the role of getting you from position and momentum space. It's a Fourier transform. So momentum you can think about as velocity in some sense, and position is just position. And they're related by a Fourier transform. And what Heisenberg said, look, you cannot know position and momentum at the same time. In fact, it goes on to say, if I know exactly the position of a particle, I have no idea about its velocity, like zero information. Okay? That, in some sense, is that picture. I know exactly where it is in time. No idea about its frequency. On the other hand, if you say, I know exactly how fast this particle is moving, right? I calculate it out exactly. Then you have no idea where it is, actually. That's this picture. I know exactly how fast it's moving. I have no idea where it is. What does this time frequency representation do? The Gabor transform says, I'm going to keep time information by windowing. And ultimately, what I'm going to do with this window as I slide it around is I'm going to resolve time somehow. But for each slice of time, I'm going to Fourier transform that window and calculate the frequency content in that window. So here's the idea. You bin up both frequency and time with some certain resolution. And for instance, you can ask the following question. I have a signal, and I can ask, what is the frequency content at some time? So I can ask about what's the frequency content that I want for these frequencies at this given time. And I can go up there and look. Whereas this picture here, I can't even quantify time in the Fourier domain. Or here I can quantify time, but I have no idea about what its frequency components are. Right? So this gives you a way of getting both information and time and space. And by the way, the size of these boxes are related to Heisenberg uncertainty. This cartoon is really important for you to understand. Right? There's nothing quantitative here. It's a qualitative way to think about time frequency analysis, but that's where we're going. Right there. Everybody okay with that? Does that make sense? That's the cartoon. Everybody can draw it. If I said draw a cartoon on the final, that's the one you draw. You don't draw a duck or a whale. I mean, you might want to draw the lake whale. I understand. But at least put checkerboard pattern on him or something. Her. Whoever that lake whale is. Okay. Everybody good with that? That's it. Yeah.
If you divide up your time really finely, then you would have a really hard time seeing really low frequencies, wouldn't you?
You certainly would. In fact, we're going to talk about the limitations of this windowing issue. Because ultimately, the Gabor transform leaves one unsatisfied for the following reason. So here's the point that Jake's making. We'll come to this a little more. You can say, I really want to get out good resolution of both frequency and space. So you have a choice about, well, sliding is easy. I can continuously slide it. I can decide how finely when I slide it. But you decide on, do I want a window that's like this, or do I want a window that's like this? So first of all, it's a Fourier transform. What frequencies fit in here? Or what wavelengths? Well, you know, the longest wavelength that fits in that box is that. But look, there's some pretty big trends in this. Low frequency stuff that's sitting in your signal. And by choosing your window this length, what do you do with all those frequencies? They no longer exist. Because you've picked a window, right? So whatever your window size, you say, yeah, but I get really good resolution of high frequencies, right? Because I took a little window and I can resolve fine scale and time right there. And I've thrown out all my low frequencies. Okay, so, all right, well, what about if I make a big window? Well, the big window is kind of nice because now I get some of the big low frequency stuff. But because I've taken a big window, I've lost localization of in time of these peaks that are there. Right? So there's some real issues with this. Okay, the obvious solution to this, in some sense, if you just had time to think about it for a while, if I put you in a room and say, think about about this, and I'll unlock the room when you come up with something that sounds reasonable to do. You would probably come up with this, which is, well, couldn't I take the single signal and like analyze it in different ways and like maybe take a big box and a small box, and then so I'd get some, you know, I can get the low frequencies like that and the high frequencies like this by shifting my, yes! I would say you, maybe not that forcefully. I'd let you out for sure. But first I'd see if your dog lived. And then maybe, and if your dog hadn't lived yet, I'd keep you in the room until your dog, you know, you found that marble. Okay, but that's what you would do, and that's where we're going to go next, at least on this afternoon from 4 to 5. See, this is like the previews for this afternoon show. I mean, you guys are, I know you probably want the lecture to be right at 9:30, not 4, because you can't wait, right? But 4 o'clock, wavelets, talks all about that. But at least in the short time, Fourier transform as defined, whatever you pick your window size to be, you automatically have limitations. You throw away a bunch of information because you are not accounting for the fact that I cannot simultaneously get long frequencies and short frequencies with a given window, right? I could try to get the best of both worlds. That's what you're really trying to do here. But ultimately, if you really need good resolution at both low and high frequencies, you got to move away from this. Okay? But still, this was very useful. 1946 set up the whole business of radar detection, kind of took a huge leap forward because people started thinking about now, is there a target there? I have something moving around. I'm not just filtering this thing, maybe even to try to disguise our frequency. Now I can just take this information I keep getting in, plot it in time and frequency. I get localization of the target and its frequency, and I can start doing some testing about what stuff, if it sits there or not. Okay. So this is the continuous Gabor transform that I introduced. Okay. And by the way, Gabor, what he actually did when he did this work originally, he took this G to be a Gaussian with some scalings. Okay. And in taking this to be a Gaussian, the application in quantum mechanics gave him what are called coherent quantum states. Okay, so the discrete Gabor transform, his original, or some of his original work in that was in quantum mechanics, the interpretation of these probability states, and what this pulls out is a small window of time, and you could start talking about what are called the little waves that are in there, captured in little windows of time, and they call those coherent quantum states, for instance. Okay, and that's actually a nice one. The Gaussian is always a nice thing to start with. Okay, just like in the homework, you guys did Gaussian, probably did Gaussian. I didn't make you do Gaussian. You could do any filter you want, right? I didn't say you had to do a filter. But you know, one I did in class last Friday was a Gaussian filter, because it's just so simple, right? Smooth, nice properties. Okay, but this is the discrete Gabor transform. Now we're going to move on to, sorry, that was the continuous Gabor transform. Now it's the discrete. I'm getting ahead of myself. So ultimately, this is what we do computationally, right? Theory, yes, it's nice to do a continuous transform for a continuous variable. When we actually go to apply this in practice in a code, it's going to be discrete at some lattice points. So for instance, you might sample at different points in time and different points in space and frequency, okay? And you're going to define this Gabor transform as e to the I 2 pi m omega naught t. Okay, so you're shifting this Gaussian, let's say, around by nt naught integer values, okay, just like you would in a computational scheme. And you're shifting the frequency here by multiples of omega naught, okay? So ultimately, this might look something like this. So for instance, you might have a Gaussian, and you shift it over by t naught. And over here, it'd be shifted over by nt naught, for instance. This is with m equals 0. Or you might take this thing, you might shift it And now you're looking at something like this, where m is not 0. Right? M is not 0. This is just an oscillating sine cosine function. You take this, you would shift this over, or you shift it over here. So it's shifted over by n t naught, and it's e to the I 2 pi m omega naught. So things like this. These are the basic functions you could be working with to look at this thing. And the Gabor transform from this is defined in the same way. But the idea here is you put it on a discrete lattice. So here, remember, when you look at this thing, this is for a continuous t and a continuous omega. And all you're saying is like, well, no, now I'm going to discretize t and omega. Same definition of the transform. It's just that now you are doing it at very specific time points and very specific spectral points. It looks a lot like this cartoon here. So when I draw the boxes, these are my different omega values that I discretize at different t values. Okay? All right. So otherwise, the lines would make sense. It'd be more a continuum. Okay? All right. Things I won't talk about. There are other methods, by the way, and I'll have it in the notes. I'll put it in there just as for completeness. But in addition to these short-time Fourier transforms such as this, there are other time frequency methods, windowed Fourier transform methods out there. Two of the most popular ones. One of them is called the Zach transform. The other one that I'll mention is the Wigner-Will. Now, Wigner-Will, by the way, is a nonlinear transform. And also, the Wigner-Will has this interesting property that Wigner-Will is actually the one that kind of really took off on radar, took off for radar. There's some very nice properties that it has that allows it to have good time, frequency localization, and it actually was the one that radar sort of started going off on. Okay, so those are some other ones. Final comments then. Nice method. A first pass, right? Historically, here's a first way we can think about, a very easy way to think about having both time and frequency information simultaneously. That's what you want, right? I want to detect a target. I want to know where it is. If I'm in a song, I want to know what the frequency components are played at different times, so that if I'm at home playing Guitar Hero, I know what I got to be doing in time. And we got a big screen TV and Guitar Hero. That's how we're going to end this class right here. Right here, see? Bring it up Friday, last day of class, we're going to all play Guitar Hero. And it'll be all about time frequency analysis, right? It'll be super sweet. And then we'll all realize how important it is to be on the beat, because you get more points, right? Is that right? See? All right. Final thing, though, there's some severe shortcomings to this, right? Whatever window you pick, because of this, at least the first pass, the Gabor window is fixed, right? It's width A. You slide it around. Because you have a fixed width, you miss a lot. The fixed width tells you, if I make it wider, I miss a lot of time localization. If I make it very narrow, I miss all low frequency components. No matter what you do with this kind of information, you're throwing away a lot of information, either high frequency or lower frequency or time. So there's some serious drawbacks to it. Again, it gives you some information, and the idea is that we can do much better. And the wavelet idea, right? The wavelet idea is just basically they said, hey, well, why don't we do better by just keep changing the width of that window? First, pull out the big scale stuff, big fluctuations with a big window. I don't care about the fine scale. Why? Because you know what I'm going to do next? I'm going to cut that window in half and then ask what's there. Cut it in half again, ask what's there. Cut it in half again. And as I progressively do this, I get finer and finer scale structure. And I don't care anymore, because I already did a pass on it, and I already took out all the big scale stuff. The next one, it takes finer and finer and finer scale. It's called a multi-resolution analysis. So we're going to talk about at 4. Hey, welcome back. Thanks. Good to see you guys. I'll see you at 4, if not earlier, maybe at the Nobel Prize lecture that I'm giving. Did I say I was giving Nobel Prize lecture? Anyway, I'm going to give that at 2:30. See you Friday. Have a good weekend if I don't see you.